Chapter 13, we are going to talk about solutions. And then really in section 13.1, we are going to be talking about solutions, and in 13.1 specifically, kind of reviewing, for the most part, things that we learned about solutions last year. So if we start with that review, solutions are homogeneous mixtures of two or more pure substances. So remember, homogeneous is really a solution that exists in one phase. So below there's a few examples of great solutions. So a gas dissolved in a gas, a liquid dissolved in a gas, a solid dissolved in a gas. All sorts of examples. So that you can look at down below. Mostly, for the most part, when we deal with solutions, we're dealing with a liquid dissolved in a liquid, sometimes a gas dissolved in a liquid, and most of the times it's solids dissolved in liquids. But solution is a one-phase mixture. Now, when we talk about solutions, we're going to hear the word solute and solvent. Remember, solute is what's being dissolved, solvent is what's doing the dissolving. Now, if we explore this from our intermolecular force standpoint, which we talked about in Chapter 11, how a solution works, essentially, there are forces between the solute and solvent particles, and they have to be strong enough to compete with the solute particles. They're really going to compete. Those forces are going to compete against one another. The solvent is going to pull around the solute, and it's going to surround them. And the word for that is when the solvent surrounds the solute, it's called solvates. So a little new vocabulary word there. Solvates is when the solvent surrounds the solute, which you can see there. Now, how does the solution form? If it's ionic salt and water, the ion or the dipole interactions are strong enough to overcome the lattice energy of the salt crystal. They're going to break apart and form ions in solution. Now, if we talk about energy changes in solution, it's really it's a three-step energy process. There's three ways in which enthalpy is being formed in a solution. And if you look at the diagram does a great job on this. First, there's the enthalpy or the heat needed to separate the solute molecules. 2, there's energy needed to separate the solvent molecules. And then 3, there's energy needed for them to interact and have these solvent molecules surround the solute molecules. So there's 3 different enthalpies needed in a solution. 1 to surround or break up the solute, 1 to break up the solvent, and then 1 to have the solvent and the solute interact with one another. And if we look at this at a diagram, what we're going to have is the enthalpy change for the overall change in solution. So typically, the solvent and solute breaking apart are one energy, and then when they interact, it's the third energy. The difference between those three is your net exothermic reaction. So you can, again, on the right-hand side here, you can show what happens if the energy is less. So why do endothermic processes occur? Well, here's the key, or here's kind of the word that we're going to talk about now, and we're going to talk about it a little bit more when we talk about thermodynamics, and that word is focused on entropy. So entropy, we're going to get there in a second. So we know in some processes heat is absorbed, not released. Well, how the heck does that work? Well, here it comes. We talk about entropy. And what entropy is the randomness or disorder in a system. And here's the general rule. Systems like more entropy. They typically like more disorder. All right, things in the universe are not ordered. So if we look at the picture A on the top, does picture A ever exist in real life? Think about it. If you mix two solutions together, do they stay on separate sides of the container? All right, no. Picture A on top with the 500 milliliters of carbon tetrachloride and the 500 milliliters of propane. That's not propane. That's hexane. Hexane, excuse me. If they All right, they're never going to be like that. They're going to mix, and when they mix, they're going to increase randomness or increase the disorder in the solution, and that's increasing entropy. The universe favors entropy. It favors disorder. So, how does this work? While entropy may increase, the system can decrease if the system becomes more disordered. So sometimes enthalpy will be affected by entropy, and we're going to talk about this a little bit more when we start talking about thermodynamics. Now, one thing we have to talk about and be aware about is just because something disappears when it comes into contact with a solvent doesn't mean the substance is dissolved. It's very possible you can get it back. And this process that you kind of have to be aware about is called dissolution. Dissolution is a physical change, not a chemical change. So what is dissolution? If you can get back the original solute by evaporating the solvent, all right, if you did that, it didn't dissolve. If you can't, the substance didn't dissolve, it reacted. So if something simply dissolves, you're going to be able to evaporate the solvent and get it back. However, if you evaporate it and don't get it back, then you had a chemical reaction occur. So something to be on the lookout for. So just a little heads up there. All right, when we talk about types of solutions, remember, there are three types of solutions. There are unsaturated, saturated, and supersaturated. Saturated is the solvent is holding as much solute as it possibly can. Unsaturated means it can hold more, and supersaturated means that for a particular, the forces are, supersaturated means that it's holding more than it possibly can. All right, and that's possible if you can heat up the solution and fit more in when the molecules are moving faster, but supersaturated. So saturated is pertaining to a particular temperature. Remember, you can get solutions that are supersaturated if you heat them up. Now, unsaturated is very simple. It's holding less than what you know can hold at a particular temperature. And then supersaturated, in saturated solutions, the solvent holds more solute than it normally can at a possible temperature. Now, when it does this, this is very unstable, and crystallization can happen at any time if you drop a seed crystal in. I will do a demo in class when we talk about this, so you can kind of get the idea of how this works, a seed crystal and forming crystals. Very, very cool process. All right. Last thing that we need to talk about, reviewing solutions. We've talked about saturated, unsaturated, supersaturated. We've talked about homogeneous solutions. We added a little bit with entropy and enthalpy. The last thing that we need to talk about is what affects solubility. What affects how things are going to dissolve. And remember, we learned this last year, the saying like dissolves like. So polar substances dissolve in polar solvents. Nonpolar substances dissolve in nonpolar solvents. So polar, polar, nonpolar, nonpolar. Just a very easy way to remember like dissolves like. Now, the more similar the intermolecular attractions, the more likely one substance is to be soluble in another. So for example, glucose, which has hydrogen bonding, is very soluble in water. Why? Water also has hydrogen bonding. All right, so glucose, which has hydrogen bonding, is soluble in water, which has hydrogen bonding. However, cyclohexane, which only has dispersion forces, or remember London dispersion forces, it's not, because glucose has hydrogen bonding more than the dispersion forces. So their forces don't match up, and that's why they don't really dissolve as well. So vitamin A is soluble in nonpolar compounds like fats, where vitamin C is soluble in water. And if you take a nutrition class or a biochemistry class, they're going to talk about the differences in some vitamins are fat soluble and some are water soluble, and kind of the differences in their molecular arrangements that affect solubility. Now, we talk about gases in solution. Gases kind of defy a few laws, all right? And not defy, I shouldn't say defy, but the reasoning on gases is opposite of that of liquids or solids. So gases in water increase, the solubility of gases in water increase with increasing mass. So the heavier the gases, the more easier they are dissolved in water. because larger molecules have stronger dispersion forces, which we talked about in Chapter 11. Now, gases in solution. The solubility of liquids and solids does not change with pressure. All right? Liquids and solids, the solubility does not change with pressure. However, gases do. The solubility of a gas in a liquid is directly proportional to its pressure. Think about a can of pop. Why is a can of pop stored under pressure? All right, that's so that carbon dioxide stays dissolved in your can of pop. What happens after a couple hours once that can of pop is open? All right, that pressure is no longer maintained in the bottle, and the solubility of the gas decreases very quickly, and your pop goes flat. So just an idea of gases. Gases their solubility is related to pressure. And what we'll do is there's an equation to kind of figure out the solubility of a gas. There are Sg is equal to K times Pg. And we have the following three things here. Sg is the solubility of the gas. K is a constant. That means that you will look it up. You never have to look up constants. They're always given to you. K is a constant for the gas in the solvent. So depending on the gas will depend on the K value, and Pg is the partial pressure of the gas above the liquid. So a lot of times you'll be given K, obviously, and either Sg or Pg, and asked to solve for Sg or Pg. And we'll do a couple of those examples in class. Last thing when we are talking about solubility, a couple things that affect solubility. Temperature. Generally, the solubility of solids in liquids, so when a solid dissolves in liquid, increases with increasing temperature. Now there are a few exceptions, but if you look at this curve, mostly the solubility increases when the temperature increases, for the exception of cesium sulfate. So just an idea there, or an idea. The opposite is true for gases. So remember how gases are kind of the opposites. Typically, gases dissolve better when they are colder. Think about it. Why does pop taste better when it's colder? It's because it has more of a carbonated feeling. The carbonation is more saturated. Warm lakes have less O2 than in cool lakes. So in Minnesota, when our lakes get cool in the winter, it does fish a favor by really increasing the amount of oxygen in the lake, if you think of it that way. All right, so temperature was kind of the last thing. So gases, remember, the solubility of gases and liquids increases under pressure and increases when it gets cooler. The opposite is said for liquids and solids. Typically, less pressure doesn't affect liquids and solids concentration, and for temperature, especially when we're talking about solids being dissolved in liquids, warmer is better. So make sure you're able to distinguish the two. And that kind of concludes our review on 13.1 and our review of solution.